Hello and welcome to another lesson in Math 1106, Math for Business Precalculus. My name is John Adamski. This is week 8. We're going to be studying linear functions. Last week we discussed the xy plane and the Cartesian coordinate system. This week we're going to put a line in the xy plane and discuss how we can use the coordinate system to define something called the slope of a line. And from that we'll be able to derive a certain type of equation whose graph is a line. And we'll use that to define what we mean by a linear function. And once we have the idea of a linear function, we'll quickly look at some applications of how you can use linear functions in the study of nonlinear functions. Linear functions pop up all the time. We'll look at equations of secant lines, average rate of change, and we'll wrap up with the topic of linear models, where we'll use linear functions to model a business scenario for a small business, how you could model, say, the cost and revenue of a small business with linear functions. So let's get to it. Let's start with 2 points in the xy plane. Let's say I have x1, y1 here and x2, y2 here. I'm just referring to their coordinates as x1, y1, x2, y2. This is the first point, the second point. Those 2 points determine a line in the sense that there is only one line segment connecting the points, and if I extend that line segment infinitely far in both directions, that gives me a line. So we're looking at the line through these 2 points. If you give me those 2 points, there's a unique line through those 2 points. There's not any other, there's only one. Here it is. And I can define the slope of the line that passes through those 2 points. It's defined in terms of the coordinates of these points. We use the letter m typically for slope. M is equal to y2 minus y1 over x2 minus x1. This is often referred to as change in y over change in x because I'm looking at the difference between 2 y coordinates over the difference between the 2 x coordinates. This is how it's calculated. And in my picture, when I draw a horizontal line from here to here and a vertical line from here to here, I've created a right triangle. And the height of that triangle is the change in y. It is the difference between their y coordinates. This distance right here is the exact same as this distance right here. And along a number line, we can compute the distance by just taking y2 minus y1. This is y2 minus y1. And similarly, the base of this triangle, the horizontal distance between those 2 points, is the same as the horizontal distance along the x-axis from x1 to x2. This is the change in the x coordinates, and it's x2 minus x1. And when we calculate slope, we're taking this height divided by this base. Okay? That's what this is coming from. That's the calculation. That's the slope of this line connecting those 2 points. Now, we're talking about the slope of a line. It shouldn't really depend on which particular points you look at, and it actually doesn't. Here we have a line. It looks very similar to the other line. I don't have any points marked out, but if I just pick any 2, say this point and this point, and do the same sort of thing, look at what is the difference between their x coordinates and the difference between their y coordinates, I can compute the lengths of these legs of this right triangle, and regardless of what 2 points I pick, that ratio is going to be the same for any 2 points. I'm just showing you with a couple different pairs of points how I can compute similar triangles. And actually, those triangles are similar in the sense that they are all proportional to one another. In other words, all of these triangles that I've drawn have 90-degree angles in one of their corners. This is where vertical lines and horizontal lines meet. And they also have one of their angles up above, where a horizontal line meets this, this orange line, and that's going to be the same angle for every one of these triangles. And the third angle is then necessarily the same. It's also easy to see that that's where a vertical line meets the orange line, and those are all going to be the same angle for every single one of these triangles. So of all the triangles that I just drew, they have all of them have all 3 angles the same. That means that the only difference between any 2 of those triangles is how much they've been scaled by. They're all proportional. Okay? They're not distortions of one another. Some may be bigger and some may be smaller, but they've been stretched equally in the horizontal and the vertical direction. Those are what we call similar triangles. And in other words, if you were to take the height of any one of those triangles and divide it by the base, you would get the same number for any one of those triangles. Okay, that's what it means to say that these triangles are proportional to one another. And so that number, height divided by base, that seems to come from the line and does not depend on which 2 points you pick, is a property of the line. We call it the slope, and this is where it's coming from. Okay, so as a quick example, you should be able to calculate the slope of a line that passes through 2 given points. We have the formula for it right here, so it should be pretty simple. It doesn't matter which one you consider to be the first point. I'll say this is the first point, so x1 is -2, y1 is 1. And which one is the second point? I'll say here's x2, y2. But you could switch these and you get the same answer. The calculation for slope, I'll just write it down. We've got y2 minus y1 divided by x2 minus x1. That's going to be 3 minus 1 upstairs, 3 minus 1, divided by 4 minus -2, so 4 minus -2. I get 2 divided by, this is 4 plus 2, so that's a 6. I'll reduce that to be 1/3, but that's the answer. That would be the slope of this line. Here's another example that may help us better understand what information is contained in the slope of a line. So this says, suppose a line passes through the point 2, 5. Here's the point 2, 5. If the slope of the line is 1/2, tell me 6 more points on the line. Okay, the slope is 1/2. Well, we understand that the slope is this ratio of change in y over change in x, and we're told that that's 1/2. Okay? So the way I'm going to interpret that is to mean that the change in x is 2 and the change in y is 1. That's kind of what this expression is telling me, right? That this ratio of change in y over change in x is 1/2. So if change in y is 1 and change in x is 2, that certainly matches what this is saying. And I can interpret this as a set of instructions as how to get from this point on the line to other points on the line. When I say change in x is 2, I'm just going to change x by +2. That is to say, I'm going to add 2. So I'll get 4, 6, 8. Of course, I could keep going. At the same time, I'm going to change y. And the way that I'm going to change y is, well, by +1. I'm going to add 1. So I'm going to go from 5 to 6 to 7 to 8. Okay? Now, if we look at where those points are, let's plot them. We've got 2, 5. Here's 4, 6. So I go over to 4, 6. That would be right here. 6, 7. That would be 5, 6, 7. That would be up here. Okay, 8, 8 is way over here. They're following a pattern. Okay, we're going to the right by 2 and up by 1 every single time. That's a change in x over a change in y over change in x. Okay, that slope of 1/2 can also be interpreted, let's see, we could say that change in y over change in x, it's 1/2, but you can write 1/2 in other ways. You could write it as -1 over -2. That's also the fraction 1/2. That's another way of writing it. Now I'm interpreting, I'll say that change in x is -1 and change in y is, change in x is -2, change in y is -1. So I'm going to change x by -2. That means I'm going to go down to 0, -2, -4. Meanwhile, I'm going to change y by -1. We're going to go to 4, 3, 2. Okay, so we changed x by -2. We changed y by -1. That produced more points. Where are those? Well, let's see. 0, 4. That would be 0, 4 would be here. -2, 3. -2, 3 would be here. -4, 2 would be right about here. And you'll notice that all those points are on the same line. Okay, it's not drawn perfectly, but that's the idea. Okay, we can continue this line to the right and up. We can continue it to the left and down, following the slope as a set of instructions for generating more points on the line. Okay? If the slope was negative 1/2, then what? Well, we can play the same sort of game. If change in y over change in x is negative 1/2, that generates a set of instructions for getting more points on the line. I'll say delta x is 2, and delta y is negative 1. Okay? Maybe I'll put it over here. Delta y is negative 1. So, since delta x is positive 2, I'm going to add 2 to the x coordinates. I'll get 4, 6, and 8. Since delta y is negative 1, I'll subtract 1 from the y coordinates. I'll get 4, 3, 2. That gives me a whole bunch of more points on the line. Let's just plot a couple of them. 4, 4, that would be, let's see, 4, 4 would be here. 6, 3, that would be 6, 3 right here. Okay, and 8, 2, that would be all the way over here. That's me extending the line in this direction. Okay, and if I interpret the slope a little bit differently, now let's say that change in y over change in x, I know that it's negative 1/2, but I didn't have to write negative 1/2. I could have written 1 over negative 2. And that would be a different sort of set of instructions, where now I'm saying delta x is negative 2 and delta y is positive 1. So how does that affect the way I'm going to generate more points? Well, this time I'll subtract 2 from the x coordinates. I'll get 0, negative 2, negative 4. And I'll add 1 to the y coordinates. I'll get 6, 7, 8. And if I plot those points, 0, 6 would be right here. Negative 2, 7, that would be right here. Negative 2, 7 would be here. And negative 4, 8, that would be right here. And so it's continuing that line in this direction. Okay? And now that we are looking at a line with slope positive 1/2 here and negative 1/2 here, maybe we can see that there is a difference between lines with positive slope and negative slope. Lines with positive slope move in this sort of way. They move up and to the right, down and to the left. Lines with negative slope behave differently. Negative slope lines, they move up and to the left, down and to the right. Okay, so at a glance, you can tell whether the slope of a line is positive or negative simply based on how it's slanted, whether it goes up and to the right or whether it goes down and to the right. Okay, to actually calculate numerically what the slope is, you have to get down and look at 2 points on it and calculate it according to the formula for slope. But positive and negative you can see at a glance. Now, in last week's lesson, we talked about how an equation involving the variables x and y describes a set of points in the plane called a graph, and how the graph of an equation is generally a curve in the plane. But a natural question to ask is, well, if you started with a line in the plane, is there an equation that describes that line? Is there an equation in x and y whose graph is that line? I'm talking about the equations of lines. And so before we get into the general equation of a line, let's look at some really easy examples. Because of the way that the xy plane is oriented with an x-axis, a horizontal x-axis, and a vertical y-axis, it's very easy to describe vertical and horizontal lines. A vertical line, here's one. A vertical line has a very simple equation. If you just think about what points would be on this line, well, since it's vertical, all of the points on this line have the exact same x coordinate. So I'm saying the x coordinate is c. And you can see that this line passes through the x-axis at c. Its x-intercept is c. I chose to have points whose y-coordinates are 1 and 3. But all of the points on this line have different y-coordinates, but they all have the same x-coordinate. Their x-coordinate is c. That's what determines whether you're on this line. If your x-coordinate is c, you're on this line. And it doesn't matter what your y-coordinate is. If your x-coordinate is c, you're on this line. So this is the equation that describes that line. On the other hand, if we look at horizontal lines, here's one. Every single point on this line has the exact same y-coordinate. I've got it labeled c. So every point on this line has the same y-coordinate c. And that's what determines whether a point is on this line or not. If a point's y coordinate is c, it's on this line, and its x coordinate could literally be anything. That doesn't matter. As long as its y coordinate is c, you're on the line. So the equation for that line is very simple. It's just y equals c. Now, what are the slopes of these lines? Well, if we try and calculate the slope of a horizontal line, there's not really any problem. I've got 2 points on this line right here, 2c, 4c. I'll take the difference of their y coordinates. That would be c minus c. I'll take the difference of their x coordinates. That would be 4 minus 2. And I get the answer of 0 over 2. Well, that's fine. That's 0. The slope of a horizontal line is 0. It's always going to be 0 because when you look at any 2 points on a horizontal line, their y coordinates are the same, and the change in y is always 0. When you look at a vertical line, the story is a little bit different. Now I've got 2 points on a vertical line. I have their y coordinates as 3 and 1. We can calculate the change in y as 3 minus 1. But their x coordinates are exactly the same. So you're going to get c minus c. And this is going to be a problem because you have 2 divided by 0. You cannot divide by 0. When a fraction has 0 in its denominator, it's undefined. So the slope of a horizontal line is 0. That's fine. And that actually makes sense because the horizontal line is not slanted up in the positive slope direction or slanted down in the negative slope direction. It's kind of right in the middle. And what is the number that's right in between positive and negative? It would be 0. So this is making great sense. The vertical line is a little bit weird. It doesn't have a defined slope. It breaks the mold. So if you happen to be talking about a vertical line, then you're talking about the one and only type of line that does not have a slope. It has an undefined slope. But let's move on from those sort of exceptional cases of vertical and horizontal lines whose equations are very simple. And let's look at another line with any other slope. Okay? Let L be a line that passes through this particular point, x1, y1, with slope m. So this point and this number have been provided. I'm trying to develop an equation for this line. Okay? So imagine xy is any other point on this line. Okay? I've picked out this one just for visual purposes, but it could be any point on this line. What could you say? Well, since we know that the slope is m, I know that if I were to compute the change in x and the change in y, the change in x would be the difference between the x coordinates. That would be x minus x1. And the change in y, the difference between the y coordinates, would be y minus y1. So I could go ahead and calculate those. And that ratio of change in y over change in x should equal m. This is the equation that I'm talking about. This is an equation involving x and y. Remember that x1, y1, and m are constants that have been provided. X and y are the variables. And the points x, y that satisfy this equation are on this line. And the points that aren't on the line don't satisfy this equation. If you connected this point to a point that wasn't on the line, you would calculate this ratio of change in y over change in x, and you would not get m. Okay? So this is an equation satisfied by points on the line, not satisfied by points not on the line. This is the equation of a line. It's not the usual way that we write it because it can be written without denominators, and that's usually preferable. So if I multiply both sides by x minus x1, I go from this form to this form of the same equation. And this has a name. This is called the point-slope equation of the line through the point x1, y1 with slope m. And this is one that you're going to want to have memorized if you don't already, because it makes it so easy to write down immediately the equation of a line given this basic information about it, which you often have at hand. So this is one to memorize. Let's get some practice using the point-slope equation in answering this question. It says, given equation for the line through the given point with the given slope. The given point is 6, negative 1. The slope is 5, 6. This is the exact scenario that I use the point-slope equation for because I have the given point, I have the given slope. This is my template. I just have to plug in and use it. You have to, make sure you realize that this is x1 and y1. Those are the coordinates of the given point. Obviously, this is the slope. So I think I'm ready to just plug right into this. It's going to look like y minus -1 equals m 5/6 times x minus 6. Don't forget the parentheses on the right-hand side. That's important. If I were going to go any further, maybe I would distribute this 5/6. That would be something I could do, but you don't have to do that. If it just says to give an equation, this is a perfectly fine equation, I'm just going to leave it like that, at least for now. In the second example, let's see what this one looks like. It's the same idea. I've been given x1 is 0, y1 is 4, so my point slope equation is going to look like this. It's going to look like y minus 4 equals m, that's -2/3, times x minus 0. Well, x minus 0 is just x, so this time I can just leave it as x. Okay? And this one I can kind of see there's a nice way to simplify this. I can solve it for y and write y equals -2/3 x plus 4. Okay, that has a nice look to it. I could have actually gone ahead and done that with this example also. Maybe let's do that. If I distribute this 5/6, you're going to see that this right-hand side is 5/6 x minus 5/6 times 6. Those 6's are going to cancel. I'm just going to leave behind a -5. Now you have y plus 1 equals, maybe I'll write it down over here, y plus 1 is the left-hand side, and the right-hand side is 5/6 x minus 5. Okay? If you subtract 1 from both sides, then you can write this in the form y equals 5/6 x minus 6. Now that's the same equation as this one in that it has the same exact solutions. So both this answer and this answer both describe the line and answer the question. I can't deny that this one looks a little bit cleaner, a little bit simpler. And since every line can also be put in this form, it has a name. This is the slope-intercept equation. Why? Well, the two numbers that I see here on the right, 5/6 is the slope of the line. The coefficient of x is the slope of the line. And this constant term on the right, that's the y-intercept. And you can figure that out by setting x equal to 0 and finding out that y is -6. So this line goes through the y-axis at -6. And it has a slope of 5/6, which is a positive slope. So this line would look something like this. Okay? This is a convenient way of writing it. It conveys a few important details at a glance. So it has a name. It's the slope-intercept equation. Again, the coefficient of x is the slope, and the constant term at the end is the y-intercept. And this equation is kind of nice. It has the form y equals a function of x. What I'm saying is you can think of this right-hand side as a function of x. There's no y's over here. It's a function of x, and it's a very simple function of x. It's what we call a linear function. A linear function is any function of the form mx plus b. So you take your variable, you don't raise it to any powers or any root. You have your variable times a number, a coefficient, plus a constant, and that's it. And we don't want that coefficient to be 0. If m were 0, then this term would go away, and your function would actually be a constant. The function would output b no matter what x is. With a non-zero m, this is now what we call a linear function of x. Notice that there are no exponents. X does not appear in any denominators. There are no square roots. This is a very simple function, almost the simplest other than a constant. It's called a linear function. Here's another question about equations of lines. It says, find the x and y intercept and the slope of the line with this equation. Now, I know that this equation has a graph, and it makes sense to ask what the x and y intercept of that graph are. But it seems to imply that this graph is a line. Can we verify that this equation does define a line? Well, I can if I manipulate it. If I can put it in the form y equals mx plus b, that we just talked about. That would be the graph of a linear function, and a linear function's graph is a line. So can you make it look like this? The answer is yes. I just need to solve this for y. If I bring the 4x to the other side, I see that this is equal to negative 4x plus 5. And if I divide both sides by negative 2, like this, I get y alone by itself on the left-hand side. And on the right-hand side, you have negative 4x divided by negative 2. That's a 2x. And a 5 divided by negative 2, that's a minus 5/2. Okay? You could leave it like this, but I'm splitting the fraction up and performing the division. And so this is the same, this is an equivalent equation. It has the exact same solutions as the equation that I started with. But now I recognize that it has the form y equals mx plus b. And I know that the graph of this equation is therefore a line, because it's the graph of a linear function. Okay? Since I did that work, I can read off for you the slope and the y-intercept right away. That's what these numbers 2 and negative 5/2 are. So the y-intercept is negative 5/2. Maybe to emphasize that that's on the y-axis, I'll say the x-coordinate is 0. The y-coordinate is negative 5/2. That's the y-intercept. The slope, which I can also see right away at a glance, is 2. Maybe I'll just say m equals 2. Now what about the x-intercept? That's not obvious from this form or this form, though I think I'd prefer to work with this in the original equation that I was handed. If you want to know where what the x-intercept is, you're just going to set y equal to 0 and solve for x. If y is 0, this term goes away. We end up with the equation 4x equals 5, and if I divide both sides by 4, I find out that x is equal to 5/4. So what does that tell me? That tells me that the x-intercept is a point where the y-coordinate is 0, of course. It's on the x-axis, and the x-coordinate is 5/4. Okay? That's where this question ends. I've answered the question, but let's see how this could help me to draw the graph of this equation, which we know is a line. That's important. Since I know that this is a line, it's enough to just plot 2 points on that line and then connect them with a line. Well, I can't think of any 2 points that are easier than the y-intercept and the x-intercept. So those are usually my go-to. If I'm trying to graph a linear equation, I generally find the x and y-intercepts, plot them, and then just connect them with a line. So the y-intercept is 0, negative 5/2. That's a negative 2.5 in decimals. So I'm going to go down along the y-axis to negative 2.5 or negative 5/2. And I'm going to go along the x-axis to 5/4. That's 1 1/4. So 1 and then 1/4 of the way between 1 and 2. So that's my x and y intercepts. And if I connect them with a line segment, it looks like this. And to get the entire graph, I'm going to extend that in both directions and indicate that with an arrow. This is what that line looks like. Now suppose you have a graph. Okay, suppose you have a graph y equals f of x. And maybe you're looking at it so you can see that your graph looks like this. And it's probably a curve. Okay? It's a graph in the plane. Maybe I'll label it. This is the graph y equals f of x. If you pick out 2 points on that graph, any 2 points, let's say you pick out this point here and this point here, okay? You can connect those 2 points with a line. They're just 2 points. There's a line that connects them. Would look like this. Okay? That's called a secant line. If we read the definition, it says a line that connects 2 points on a graph is called a secant line. Okay? Now, you might say that, well, if you continue that line a little bit further, maybe it intersects that graph a third time. That's okay. It still connects 2 points on the graph. Okay? That's a secant line. That's all that it is. And a typical question that you get in a calculus course is to give equations of secant lines and slopes of secant lines. So you'd be starting with some other function and talking about a secant line for that graph. Let's look at this example. It says, find the slope of the secant line connecting 2 points on the graph of this particular function, and I give you the x coordinates of those 2 points. I didn't give the y coordinates of those 2 points. We're going to need those, okay? Once you tell me what the 2 points are on the graph, it's very easy to give the equation of the line through those 2 points, okay? But what you got to understand is that the y coordinate is f of the x coordinate. So let's see. When x is 1, okay, when x is 1, y is f of 1. We're getting a point on that graph, remember? So the y coordinate is f of the x coordinate. And if I plug 1 into this function, let's see, I get -1 plus 6 is 5, minus 3 is 2. Okay, let's plot that. That's the point 1, 2. So 1, 2, that's right here. That point is on that graph. It's the point on this graph where the x coordinate is 1. Now let's do the same thing, but let's look at where x equals 4. So if x equals 4, y is f of 4. And let's see, that's going to be -16 plus 24, that's 8, minus 3 is 5. Okay, so that's another point. When x is 4, y is 5, and 4, 5 would be right here. Okay, so those are 2 points on the graph of this function. I don't need to draw the entire graph of this function. That's sort of beside the point. The secant line only depends on these 2 points. Okay, so what we're looking for is the equation of this line through those points. And now that I've got these 2 points, let me just put their coordinates here for convenience. We've got 1, 2 and 4, 5. It's easy to figure out what the slope of that secant line is. That's what the question is. Find the slope of the secant line, the slope of this line. Well, it's going to be change in y over change in x, as it always is. Our 2 y coordinates are 5 and 2, so I'll do 5 minus 2. Notice that I was taking the orange point minus the yellow point in terms of their y coordinates. I have to be consistent when I go to calculate the change in x. I also need to go to this point minus this point, same order. This time 4 minus 1. 4 minus 1. So I get 3 over 3. So I guess the slope is 1. That's the slope of the secant line. Okay? It might be helpful just to see, you don't need to know what the graph of this equation looks like, but you might know that it is a frowning face parabola. It actually looks something like this. Okay, that's the graph y equals f of x. We didn't need to know that. We didn't need to know what the shape of this graph was to answer this question. We just had to find these 2 points on the graph. Okay, those 2 points are on the graph, and the line that connects them is the secant line. We now know the slope of that line. For part B, it asks, give an equation for the secant line. Well, we know the point slope formula. It looks like this: y minus y1 equals m times x minus x1. And what do you need to know to use this? You need to know a point on the line. Do I know a point on the line? Yeah, actually I know 2. I know 2 points on the line. Let's just pick this one out of convenience. And what else do you need to know? You need to know the slope. I know that as well. So I'm good to go. I can start writing this down as it is. I'll use this as a template. We've got y minus, I'm going to use x1, y1 to be 1, 2. So y1 is 2. Equals m, that's 1, times x minus the x1 coordinate is 1. Okay, you can leave it like that if you want. That's perfectly fine. If you wanted to, you could distribute that 1 so that the right-hand side is just x minus 1. And you could add 2 to both sides to get y equals x negative 1 plus 2 is 1. So either one of these would be a perfectly fine answer. They're equivalent in the sense that they have the exact same solutions. They both have the exact same graph, which is this secant line through those 2 points. Another way to bring lines, and in particular slope, into the discussion when talking about nonlinear functions is to talk about the average rate of change. Now, the average rate of change of a function f over an interval ab is defined to be this right here. It's f of b minus f of a over b minus a, so it has a definition that you can certainly memorize. But there is a picture, and the picture is illuminating. So here is the graph of a function y equals f of x. I don't know what that function is, but this is its graph. And the interval ab, the interval from a to b, is in the domain. That's sort of built into this definition that the function should be defined between a and b. But it is, and you can certainly plug in a into your function and get out some kind of output. What the graph is showing me, the height of the graph above a, is the value of f at a. So this is the point whose x-coordinate is a. That's obvious from the graph. And the y-coordinate, since this point is on the graph y equals f of x, the y-coordinate is f of a. This point over here, it's very clear to me that its x-coordinate is b. And again, since it's on the graph y equals f of x, its y-coordinate is f of its x-coordinate. So its y-coordinate is f of b. Okay? And what am I doing when I calculate this f of b minus f of a over b minus a? Well, that is the change in these y-coordinates, right? F of b minus f of a is change in y. And b minus a is the difference between their x-coordinates. That's change in x. So you really are just calculating the slope of a secant line, of a line that connects 2 points on the graph, the 2 points whose x-coordinates are given. Okay? So we're using different language. We're not using the term secant line and points. We're talking about average rate of change over an interval, but it's coming down to the slope of a secant line. This is the same thing we were just talking about in the last example. So a typical question about average rate of change would look something like this. It says, find the average rate of change of f over the given interval. And I have two examples here. I'm changing up what is the function, what is the interval. But the calculation is always just this, okay? And it's very nice to rely on this because I don't always know what the graph looks like. It's actually probably not even helpful to try to draw these graphs and to look at the line. It's best to just compute f of b minus f of a over b minus a, and to just know that in some way we are calculating the slope of a line, the slope of a secant line connecting 2 points on this graph. But let's just get right to it. So in this case, I guess all I have to do is identify that the role of a is being played by 0, and the role of b is being played by 2. And my template says that the average rate of change is f of b minus f of a divided by b minus a. Well, let's just see what that is. So that's going to be f of 2 minus f of 0 divided by 2 minus 0. Okay? And now we just have to evaluate what are f of 2 and f of 0. F of 2 would be 2 times 2 is 4, minus 1 is 3, squared is 9, 9 minus 4 is 5, so I get 5 minus f of 0, that's going to be 1 minus 4, that's a negative 3 divided by 2. So that's an 8 divided by 2, that's a 4. Okay? The average rate of change is 4. In this example, what do we have? Well, it's going to be very similar. It's going to be f of 4 minus f of 1 divided by 4 minus 1. Okay, so what is that? F of 4 is 1/4 plus 2. Maybe just off to the side here I'll say, okay, 1/4 plus 2. Well, if you rewrite 2 using the denominator of 4, it's 8. This is 1/4 plus 2, and that's 9/4. So we get 9/4 minus f of 1. F of 1 is a nice number. 1 over 1 is 1, plus 2 is 3. So we're going to be subtracting 3. And my denominator, let's see, 4 minus 1 is 3. Okay, great. Now this is what's called a compound fraction. It's been a little while since we've seen these, but we know how to handle this. One nice thing we could do is multiply the top and the bottom by 4. The reason I'm choosing 4 is because I have this inside denominator of 4 that I would prefer to get rid of. Now, what this means is I have to multiply everything upstairs by 4 and everything downstairs also by 4. So this results in the fraction 9 minus 12 divided by 12. Okay, notice that I got rid of the inner denominator. Okay, I anticipated that. That's why I multiplied everything by 4. And now I can see what I'm left with is just negative 3 divided by 12. Both of those are multiples of 3. And if you divide the top and the bottom of that fraction by 3, you get negative 1 over 4. And that's my average rate of change. Lastly, let's step away from the geometry of graphs and lines and look at how linear functions can be applied to a problem coming from the business world. And in this setting, we'll see how the concepts of slope and intercepts, what they mean in this context. So let's just read through the question. It says, a small business finds that their monthly fixed costs are $3,000. That means regardless of how many products they make and sell, they still have to pay $3,000 just to keep the lights on. This includes rent, utilities, your fixed costs, what you're going to pay no matter what. And additionally, it costs $2.50 for each product they sell. So now to make products and sell products, it's $2.50 each. And they sell their product for $5 each. So this is how they intend to make a profit. They're selling it for more than it costs them to make it. The first question is, find a linear function for the cost of selling X products in a month. We'll do the same thing for revenue, and then we'll figure out how many products they have to sell in order to break even. But first things first, let's focus on our cost function. Okay? Now, you might be able to write this down right away, but let's think through this. Since your fixed costs are $3,000, that means that even if you're going to make 0 products, I'm using X to denote products, the number of products that you make and sell in a month. Even if you make 0 products, it still costs you $3,000 just to keep the business afloat. Okay? And when you make 1 product, well, it costs you $2.50. So now the associated cost is $3,002.50. And if you make another product, the cost goes up by another $2.50. We can see the pattern. We can stop right here. Maybe you can see what's going on here, that the slope, when we look at how I'm changing x, I'm changing x by 1. How am I changing y? The corresponding change in y is that it increases by $2.5. Okay? And so if we want to calculate the slope m, that's change in y over change in x. That's 2.5 over 1. We can see the slope is 2.5. Your cost is increasing by $2.50 every time x, the number of products sold, increases by 1. So I know that this cost function, c of x, is going to begin 2.5x mx plus b. What should b be? Well, looking at this first line, I can see that when x is 0, the cost is supposed to be 3,000. When x is 0, this term goes away. So to make the cost of producing 0 products 3,000, b has to be 3,000. So we've just figured out that our cost function is 2.5x plus 3,000. Okay? Cool. So in this context, we're not talking about slope and intercepts, really. We're saying that for each product that you make, the cost increases by this amount, 2.5. And regardless of how many products you make, your cost includes this amount of $3,000. Okay? So geometrically, we've got slope and y-intercept. But in this question, it's price per product and fixed costs. Okay. Let's do the same thing for revenue. This one's a little bit simpler. All you know about the revenue is that for every product you sell, you make $5. So if you sell 0 products, you make $0. If you sell 1 product, you make $5. If you sell 2 products, you make 10, etc. This is very simple. Maybe we can write down, maybe we can see very clearly that the revenue is simply 5x. That's it, okay? How many did you sell? You sold them for $5 each, so this is your revenue. Okay, notice that those are both linear functions. They both have the form mx plus b. In this case, b is 0. That's allowed. The last question says, how many products must be sold in a month in order to break even? Well, when are you breaking even? When you've gained enough revenue to cover your costs. Okay? So actually, you break even when your revenue is equal to your cost. That's when you've broken even, okay? When you've made enough revenue to cover your costs exactly. This equation translates into revenue equals cost. We know that those are functions of x. The revenue is 5x. The cost is 2.5x plus 3,000. This is a very simple equation to solve. It's a linear equation. If I subtract 2.5x from both sides, it says 2.5x equals 3,000. Sorry, this should say 3,000. And if I divide both sides by 2.5, you could use a calculator to do this. 3,000 divided by 2.5 is 1,200. Okay. That says that if you sell 1,200 products, you're going to get a revenue of $6,000. And if you sell 12,000 products, it's going to actually cost you $6,000 also. So this is the breaking even point. And if you start to sell more than 1,200, well, since you charge more than it costs you to make them, anything beyond 1,200, that's going to generate profit. Okay? That's where your revenue is going to start to be larger than your costs. That's the ideal scenario. Cool. So this is a nice little application of linear functions to business.